SwayamPrabha. Digital India. Educated India.
Welcome to the third lecture on basic control systems for mechanical engineers. So far in the first two lectures we have studied about systems, Laplace transform, transfer functions, and the response, particularly with respect to poles and zeros of the transfer function. From this lecture onwards we will dive more into the actual control systems. So first we will focus on understanding elements of control systems. So basically we have a plant, that is can be any system such as a car, a manufacturing machine, and which is actually it's actuated by an actuator, which could be a say a motor. Then you have some form of disturbance such as say ground vibrations. This actuator, the input to the actuator comes from a controller, and here you have your reference which the output should follow. And another important part is we have a sensor, such as maybe for position measurements such as encoder, or temperature measurements we have thermocouples, and the output of this sensor it's fed back to the controller, and the what we call the control input is modified to the plant is modified, that is manipulated by the controller. So many times what happens, instead of considering the actuator and the plant as separate, they are combined and we consider the entire dynamics. Many times the sensor dynamics is typically just considered to be one, and each of these, whether it's a plant, actuator, controller, sensor, has their own dynamics, and that is represented by simply by a transfer function which we have learnt about in the last class. So this is about what we have so far learnt is about basic elements of a control system. Now many times the you might not use the all the elements, and basically these control systems are classified into two types. One is open loop control system, where you do not have this sensor, so there is no sensor. The other one is a closed loop system which consists of this sensor and the feedback part. So what we are going to do now is consider first the open loop system. So here what we have is So here we have G represents the transfer function representing the dynamics of the plant. What we have done here is we have combined the dynamics of the actuator and the plant to get G. Next is DOL, which is the open loop controller, and since this is an open loop system with no sensor, we do not have the feedback part. Now YOL represents the open loop output, W represents the disturbance which is added to the output of the controller, and that is sent to the plant, and you have R, which is the reference. So based on what we have learnt in the last class, we can write YOL as basically G DOL R plus G times W. So we have represented YOL in terms of the reference R and disturbance W and these transfer functions of the plant as well as the open loop controller. Now if we want to write the error, which is basically the difference between the reference and the output, then we get 1 minus R minus G W, and we represent this open loop dynamics G DOL as TOL. Now that is about the open loop dynamics. Let us look at the closed loop dynamics. So let us consider controller GDCL. So this is a closed loop controller. We have the disturbance which gets added, W. And here we have the closed loop output. What we do is we feed it back, but we consider the sensor dynamics to be 1, that transfer function is equal to 1, but we have some noise which is gets added, and that is denoted by V. And this output with the noise is now added, basically subtracted from the reference to get the input for our closed loop controller, and we denote the output of the controller to be U. So we can represent this dynamics, the output YCL as GDCL plus 1 plus GDCLR plus G by 1 plus GDCLW minus GDCL by 1 plus GDCLV. Similarly to what we did for the open loop system, we can represent now the error for the closed loop system as 1 by 1 plus GDCLR minus G divided by 1 plus GDCLW plus GDCL 1 plus GDCLV, and we denote the overall transfer function for the closed loop system as GDCL divided by 1 GDCL. So now we have identified the basically the dynamics transfer functions for the open loop system and the closed loop system. Next, what we are going to do is we are going to study some important aspects of closed loops of these control systems. So, first thing we need to consider and understand is something called stability. So, for an open loop system, for stability we need that both G as well as the controller are stable. This becomes a requirement because if DOL is unstable, then we will have a very large input, and say G is unstable, then the DOL maybe you can stabilize that, but say there is a small disturbance in the form of WL, there is some uncertainty, then this DOL will grow, then the input U here will grow very large, and that is not ideal. Now, coming to the closed loop system, for stability it is necessary that we look at this TCL and ensure that as we discussed in the last class, that its poles are in the left half plane. So, basically the poles of this system TCL will basically be given by the roots of 1 plus GDCL. So, we need to ensure that this characteristic equation 1 plus GDCL is equal to 0 has basically poles in the left half plane, and we will be discussing more about stability in the next class. The next important aspect is what we call tracking. So, the idea about tracking is that the output should follow the reference as closely as possible. So, basically if we look at these two systems, the whole idea is in case of tracking is that YOL should be equal to R, or the error between the two, that is EOL, should be minimum. The same idea applies to the closed loop system, that is YCL should be equal to R, or ECL should be as minimum as possible. The next aspect is what we call regulation. The idea of regulation is our reference is basically a set point, and we want to keep the error as small as possible in the presence of disturbances. So, if we look at the open loop system, if we look at this expression for EOL, what you will see is for the disturbance W, we cannot change the contribution because it is directly just dependent on G, that is the plant transfer function. When we design a control system, the plant transfer function is fixed. The only thing we can change is the controller, which in this case is DOL. So, you will see that since you can the contribution of W to the error is just G, changing DOL does not change the error, and therefore open loop systems are not very ideal for regulation, since they cannot change the contribution of the disturbance. Now let us look at the closed loop system. Now when we come to the closed loop system, the contribution here will be G by 1 plus GDCL. Contribution of the disturbance to the error is G by 1 plus GDCL. So all we have to do is to minimize this particular quantity for a given G, is we basically increase the value of DCL. So what happens is the denominator grows large, and this overall quantity G by 1 plus GDCL will be minimized if DCL is very large. But the problem with that is, if we look at the contribution of the sensor noise, that is GDCL by 1 plus GDCL, if DCL is very large, then this quantity will increase. So making DCL large reduces the contribution of the disturbance W, but increases the contribution of the sensor noise. So we need to achieve some kind of trade-off. So we need to have some idea of what the signals W and V are. So generally what happens is sensor noise is high at high frequency. Whereas the disturbance is high at low frequency. So say we have such kind of system, then what we will do is, say we plot a graph, in the x axis is the frequency content of the, and here we have on the y axis the signal. Then what you will see is the sensor noise V looks something like this, and maybe the disturbance looks something like that. So in that case, when we are designing a controller DCL, what we will do is we will select it to be something like this, where it is high at high frequency and then it goes down. So this is basically DCL. So we need to understand what is the type of system we are dealing with, and what are the characteristics signals such as W and V, and if we have that information, we can achieve an ideal trade-off. And this can be done by some systematic techniques which we will be learning, or which you can find in the literature, or some trial and error. And the last aspect which we are going to discuss now is called the sensitivity. So the idea about sensitivity is, we are assuming that assumption is that the plant transfer function is G, but in reality it might not be G. This is the ideal case, whereas in reality we might have G plus delta G, that there is some uncertainty. So we need to understand how our design control system and our architecture, whether it's open loop or closed loop, behaves with respect to these uh, uncertainty delta G. So let us look at the open loop case. So in this case, TOL plus delta TOL is basically will be just DOL G plus delta G. So here what is there is our controller DOL is fixed, that is what we have already designed, and we look at G plus delta G, that is uncertainty in G. So in this case DOL into G is basically TOL and plus DOL delta G. Now the sensitivity of TOL with respect to G is defined as delta TOL by TOL delta G by G. So this is basically G by TOL delta TOL by delta G. Now if we look at delta TOL by TOL is basically DOL delta G by DOL into G, and from this we get it as delta G by G. So if we combine these two equations, so say this is A, this is B, we combine A and B, what we find is that S G TOL, that is the sensitivity of TOL with respect to G, is basically just equal to 1. So for an open loop system, it does not matter if whatever may be the controller DOL, you will always get the sensitivity of the open loop transfer function with respect to G to be 1. Now let us look at what happens in the closed loop case. So here basically TCL plus delta TCL will be, so wherever we had G in that transfer function, we will just insert G plus delta G, and we can express this as in terms of approximate this as the derivative. So if we do the math, what you will see is the sensitivity of the closed loop transfer function with respect to G will be so we have got this relation based on our analysis here, this, and we get the sensitivity to be 1 by 1 plus G DCL. So here you can see what's the difference from the open loop system is that this sensitivity depends on your controller which you can design. So say the first one A, this ratio this sensitivity is 0.01 and the second one is 0.001, then obviously I will select with regards to the sensitivity, I will select this controller B because it has a lower sensitivity, and that is possible because this expression of the sensitivity depends on the closed loop controller DCL, and this is a closed loop system. So far what we have studied is elements of the control system and the open loop and closed loop systems and their characteristics with regards to something about stability, tracking, regulation and sensitivity. We will be discussing more on this as we progress throughout this course. But now we will go to understanding what are the actual things about designing a controller. So, first thing we need to understand is something called time domain specifications. So, let us consider the transfer function of a simple spring mass damper system. So, here let us draw a graph representing the response of this system to a simple step input R, step is R naught. So, this is basically a R which is a step signal. Now, this system will behave, the output will look something like this. And we want to understand how what are the time domain specifications. So, the first time domain specification is what we call the rise time. So, this is used to characterize how uh, the time required by the system to reach within the vicinity of this set point R naught. So, generally, so basically time taken to reach within vicinity of set point, in which case, in this case, that is R naught, and is commonly taken from the time taken to go from 10% to 90% of R naught. So, basically what we will do, we will consider something like 0.1 R naught and 0.9 R naught, that is 10 to 90%, and we will take the corresponding time, and this time is basically rise time denoted as TR. For this simple second order system, this rise time can be approximated as 1.8 divided by omega n. Now, rise time is the first characteristic, that is the first time domain specification, which can be used to characterize the response Y of this particular system. Now, we are going to look at the next quantity, which we call the overshoot, denoted as MP. It is basically the maximum overshoot divided by the final value, often expressed as a percentage. So let us go back to our figure here. So if you look at this particular point, that is the maximum point, that is the maximum overshoot, and we divide it with respect to R naught. So you can take it something like this quantity here is a representative of MP. Basically it's this point, this value here divided by R naught. The other specification is, which is related to this maximum overshoot, is the peak time Tp. It is the time taken to reach this maximum overshoot. So the basic idea is this particular time here is basically Tp. And finally coming to the last specification, which is the settling time, denoted as Ts, is the time taken to settle within a small region of the set point. So let us go back to the figure and we say that we want this to settle, y to settle say within 1%. So in this case what we will do is we will draw something like to be within plus or minus 1% of R naught. So this is, so basically Ts, that is our settling time for the 1% case, will be the time within which it settles to this particular Ts, settles within 1%. So for example, say this is the first point where it goes within this 1% and then continues to stay within that 1%, then we'll just consider this particular time Ts. So the whole idea is it should go within the defined percentage, say 1%, and remain there for as time progresses to infinity. It could be 1%, 2% or 5%. That's up to the person who specifies these time domain specifications for the control system. So now let us derive expressions for MP, Tp and Ts. So for the overshoot, as you will see, we will need to derive what is the expression for Yt. So to go about that, we will be focusing on what we did in the last two classes. So since this is a step response, Ys will be basically h of s divided by s. If we look at the Laplace tables, we can get Yt to be of this form. Now we want to find the point where this is maximum, right? This particular point. So where Yt is maximum, so what we will do, we will set derivative of Yt to 0. So first we will compute derivative of Yt. So that will be given by this expression. So, derivative of 1 is 0 basically. So, we will start looking at this part. So, we will get this to be, first we will differentiate e to the power negative sigma t, we will get this particular expression. Next, we will differentiate the part, these cos and sine terms to get this particular expression. And now, if we simplify, we get e to the power negative sigma t, sigma square by omega t plus omega t times sine omega t t. And as we said, we will set this entire thing to be 0. So, if we look at this particular part here, it won't go to 0. So, basically we are left with sine omega t is equal to 0. And we can substitute instead of t to be Tp, that is our peak time, because that is the time when the we get the maximum overshoot. So, sine is equal to 0 implies the first time when sine will be equal to 0 is when this value omega d Tp is equal to pi. So, basically we get Tp is pi by omega t. So, this is our expression for the peak time, that is where the maximum overshoot occurs. Now, once we have this expression, we can go back to the expression for y and substitute instead of t to be Tp, and what you will get is this particular expression here. So, if we simplify this, and this can be denoted as basically 1 plus mp. So, this part corresponds to is equal to mp. Now, if we substitute from last class what we discussed about definition of sigma and omega d, where sigma is zeta omega n and omega d is omega n square root of 1 minus zeta square, we get mp can be defined as e to the power negative pi zeta divided by 1 minus zeta square, under the assumption that zeta lies between 0 and 1. So, this is our expression for mp. So, we have found basically first the peak time by finding yt, setting its derivative equal to 0. Once we have the peak time, we can just substitute the time in yt to get a overshoot percentage mp. So far we have found the expressions for, we have studied about rise time, overshoot and peak time. The final time domain specification is the settling time. Is as we discussed earlier, is the time to reach within a small region of the set point, or rather for these transients to decay down so that it will remain within a specified percentage. In this case, we have considered 1%. So, how do we derive the expression for settling time? So, we will look back at the expression for yt. So, basically it is 1 . So, we can simplify this expression to get 1 in terms of just cosine. So, we have this particular expression. Now, what you will see is, say I have some e to the power, let us consider some general expression where you have e to the power minus at sine bt, or say, since we are considering cosine here, so let us just consider a cosine signal. So, if I plot this as we have seen in the last class, when you plot this, this is a cosine signal with a varying amplitude, whose amplitude is determined by the expression e to the power minus at. So, first if I want to plot this, I will just draw e to the power minus at. E to the power minus at and minus e to the power minus at. And then within this particular envelope, I will draw my sine or cosine sinusoidal signal. So, the same way, if when there are it reaches these transients and it has to settle within these transients, that will be determined by what is the envelope basically. So, for that what we are going to do is, we are just going to consider this e to the power minus sigma t, and since we are interested in settling time Ts, we are just going to consider if it lies within 0.01. And based on that, we can take the natural log on both sides. We will get this value, negative natural log of 0.01 to be 4.6, and based on that we can find the settling time in terms of the parameters. So, Ts is 4.6 divided by sigma. So, now we have found the expressions for the overshoot peak time Ts, and we have got this expression for the rise time which we have approximated. So far we have seen for the time domain specifications and the expressions. So, how can we use this to design controllers is what we are going to understand next. So, we have seen that different time domain specifications. So, let us consider rise time that depends on omega n. We have seen that other specifications such as MP depends on zeta, and Ts settling time depends on sigma. So, now say we are given the condition that the rise time is less than or equal to some rise time Tr 0. So, this is the maximum rise time that is allowed for our system. So, under that case what happens is, what we are going to do is we are going to find the condition of omega n such that this rise time is satisfied. So, we are going to substitute the expression for Tr and we will get that omega n should be greater than or equal to 1.8 divided by Tr 0. So, we know from previously what we have discussed that for any given pole in the S plane, it is a complex number and the magnitude of which is basically omega n. So, that implies that omega n greater than is equal to 1.8 by TR0 implies that we can formulate a semicircle whose radius is equal to 1.8 by TR0, and the region outside, if we have a pole outside this semicircle, then this condition that omega n is greater than 1.8 by TR0 will be satisfied, and this holds for a second order system. Similarly, if we have MP is less than or equal to MP0, and since MP depends on zeta, we can get a condition that zeta is greater or equal to zeta 0. Now, zeta corresponds to the angle made by these poles in the S plane. So, we get the condition that we can draw a line such that its angle theta is equal to sine inverse zeta naught, and beyond this line any pole situated in this region which is marked here will be have a condition that zeta is greater than zeta 0. And similarly, for Ts less than or equal to Ts 0, we will substitute our expression for Ts in terms of sigma, and we will get sigma is greater than or equal to 4.6 divided by Ts 0. So, sigma basically corresponds to the real part of this poles. So, we can draw a line at a distance of 4.6 divided by Ts 0, and anything in this region that is on the left side of this line will satisfy this condition that sigma is greater than this value and Ts is less than some Ts 0. So, setting time will be less than Ts 0. But now you are not given this specification one at a time, but you consider all these specifications together. So, in that case what will happen is you will have something, you will have to consider all these specifications together, and what we will get is basically a composite diagram of all of these. So, here in the first case, if we consider the rise time criteria, we will have something like a semicircle on the omega n part, right. Next, if we consider the peak overshoot, we will have something of this, and if we consider the settling time, then we will have a straight line here. So, when we consider the composite diagram for all of these, what you will find is this region on these sides of these lines and the semicircle basically meets our criteria. So, if we place the poles within this region, then it will meet all the criteria as what we has been already specified. So, basically poles meet all the criteria. So now let us consider an example. So we want to find the allowable region of poles if the requirements on the system are rise time should be less than 0.6 seconds, the peak overshoot should not be more than 10%, and the settling time should be less than 3 seconds. So if we insert this into the different formulae which we just discussed, we can find that we need omega n to be greater than 3 radians per second, zeta to be greater than 0.6, and sigma to be greater than 1.53 radians per second. So now what we can do is we can consider the S plane, and basically you will find first we draw the semicircle for omega n. The next part is we consider zeta, and then we come on to sigma, which looks something. So in this case the more important criteria will be the criteria on omega n, and you will see that it depends on omega n and the criteria on the damping ratio. Sigma does not play that because it is already satisfied, it will satisfy the remaining two criteria. So this is the allowable region for poles. So far what we have studied is for a second order system. Now what happens if we have a first order system? Sorry. So let us consider a transfer function of the form sigma by s plus sigma. So basically then y of s will be h of s by s, which will be sigma divided by s plus sigma, which can be expressed using partial fractions as 1 by s minus 1 by s plus sigma. So if we go back to the Laplace tables, we can find that this is just 1 minus e to the power negative sigma t. So in this case one criteria could be the settling time. So settling time will be basically, it has to settle if we perform the same method which we did for the second order system, it will be settling time is 4.6 divided by sigma. The next criteria say is the rise time. So that will be basically just be natural log of 0.9 minus natural log of 0.1 divided by sigma is equal to 2.2 divided by sigma. This basically comes from y of t. So we find where y of t has as a value equal to 0.9 of R naught, and similarly 0.9 of the step response S, and similarly where it has a value of 0.1, and we substitute these values to get here. Now the other important aspect for this is what we call the time constant, and that is defined as tau is equal to 1 by sigma. The way that is obtained is this: we take this particular quantity is equal to 1, so we get sigma tau is equal to 1 and tau is equal to 1 by sigma. So these are the important criteria, the time domain specifications, that is the settling time, rise time and time constant for a first order system. And with that we would conclude today's lecture, where we have discussed elements of control systems and time domain specifications for second order systems and first order systems. In the next class we will focus on stability of control systems. Thank you.